Let's take a look at some hard gauge examples here. What if we have a bushing and we are trying to control the straightness of the axis of that bushing? What we note here is that we'll have a geometric tolerance on straightness, and we know that it's the straightness of the axis because of the diameter. We also note that we're using maximum material condition here. So what kind of gauging would be necessary to check this simple shape? Well, first of all, we have the go gauge, which according to the dimensional tolerance would have to be at MMC, which would be the most material, 2.15. So we create our standard go gauge, and if the bushing inserts into this go gauge, then we're saying that bushing is good. At the opposite end is the no-go gauge, and so its material condition is the least material condition. We look at the dimensional tolerance here, and the dimensional tolerance says 2.15 minus 0.15. So we end up with the smallest diameter being 2.00. And now we check whether or not the bushing fits into the gauge. Recall that if it fits, then it fails the test and the part is no good. If it doesn't fit, then we're saying the part is within tolerance. We also had the geometric tolerance, which specified a tolerance zone size based on material condition. So is it possible to create a shape gauge based upon the geometric tolerance? Well, essentially what we're going to do, as we've done before, is create a virtual condition functional gauge, and that will be based upon the maximum material condition, and because it's a external feature here, we're going to add in the width of the tolerance zone. So if you recall, the width of the tolerance zone was 0.05. So we add that in to obtain the virtual condition, and now we create a gauge at a dimension of 2.20 corresponding to that condition. Note that when we are at MMC, in other words, no deviation, then we're talking about a diameter of 2.15. So you can see here what this allows is that the bushing is not exactly straight. We could allow that axis to vary within the tolerance zone, and if it does, then the bushing will not be exactly straight. So if we look at MMC, what we see is I've got a bushing with a diameter of 2.15, and we are allowing the additional variation in terms of straightness to be 0.05. If that occurs, then it will still fit within the 2.20, and we would say that it satisfies the geometric tolerance. At LMC, that allows additional tolerance, so we have a smaller bushing, and now we are at 2.00 in terms of diameter. We have a straightness tolerance that adds the additional 0.05 plus the 0.15, and we would say that the bushing is still straight. When we evaluate the position of a hole, we're talking about locating our gauge at true position. So if you recall, true position is based upon the design specification. One of the important parts of a gauge that is checking a geometric tolerance related to position or orientation is that we have to include the datum reference frame as well as the part feature that we are trying to control. So we start with the MMC dimension, and then we either add the tolerance zone size for external features to get the virtual condition, or we would subtract it for internal features to also obtain the virtual condition. So in this example, what you see is the position of that hole that we have used before, where the tolerance zone width is 0.05, and it's based upon material condition. We also note that datums A, B, and C are not features of size, so based on that feature control frame, it is feasible to create a hard gauge to check the positional tolerance. Now what we'll have to do, of course, is create features on the gauge that correspond to, first of all, datum A, and we have to make contact with that surface first because it is primary. Then we need a surface corresponding to datum B, which would be second, and make full contact with that surface. And then finally, we need a surface in our gauge to correspond to C, which would be the tertiary, establishing the last datum. Then finally, we'll have to reflect our tolerance zone width in the size of the pin that will fit in that hole in the part. So our hard gauge here, first of all, we have to have limit gauges for all the dimensional tolerances. As we see here, we've got plus or minus, or we've got 3.5 plus 0.1 to 3.5. So we have to accommodate that with our go and no-go gauges. Go, of course, MMC, the smallest hole at 3.5, and then our no-go gauge would be 3.6 at the LMC dimension. Then we construct our virtual condition gauge for this position, and we note that we start with MMC 3.5, then we subtract out the width of the tolerance zone 0.05. And now we obtain the diameter critical dimension for our gauge for this pin to check the position of the hole. The last question that we have to answer is, where do we locate that pin with respect to surfaces, as you can see here, that we've created for A, B, and C? Well, whenever we think about position tolerance, you always have to locate the feature at true position. And as you know, the true position is with respect to your datum references. So going back to our design spec, we note that we have basic dimensions, which should be there. And of course for A, we don't need a basic dimension because that's the primary datum and it does not locate, but it orients the part. But for B, we're going to need, for the secondary, a distance of 9.5 to the center of the pin. And then for C, we're going to need a distance of 6.2. And now we've got the true position of where we will locate the pin for the gauge.